Earth freezes over like clockwork every 100,000 years. It sounds strange, doesn't it? A planet this vast, with sprawling oceans, scorching deserts, and humid jungles, somehow slipping into deep freeze on a fixed schedule, more reliable than bus timetables in many parts of the world. Picture what that would look like. Ice begins spreading from the Arctic, relentless, inch by inch, never stopping. It blankets Canada, pours into the United States, advances across Europe. Half of North America turns into a colossal white desert. Chicago, New York, Boston, all these great cities lie buried beneath ice thousands of meters thick. You could stand on that frozen surface, look down, and know that far below are mountains and valleys entombed in silence. Sea levels fall by 120 meters. What does that really mean? It means you could walk from England to France without a boat. The North Sea between them becomes dry grassland. You could trek from Siberia to Alaska on foot. Indonesia, Malaysia, and Thailand merge into a single vast landmass instead of scattered islands. The Caribbean islands rise far higher above the water than they do today. And what about the creatures of that time? Woolly mammoths, massive as trucks, roam in herds across what is now downtown Manhattan. Woolly rhinoceroses bellow across endless snowfields. Cave lions, far larger than modern lions, stalk prey through sparse forests. Giant cave bears hibernate in frozen caverns. It is an entirely different world, one we glimpse only in films and books. Then it all disappears. The ice melts, seas rise, land bridges sink beneath the waves, mammoths vanish forever. The world warms, forests return, and humans begin building civilizations. The cycle completes itself once again. For more than 100 years, scientists have wrestled with a profound question. Why? Who or what is driving this cycle? Is it the sun changing its brightness, volcanoes erupting, asteroids striking Earth, or simply chance? Tonight's journey will carry you from curiosity to astonishment, from a past hundreds of millions of years ago to a future no one can predict with certainty. We will meet the curious minds who first asked the question, the researchers who uncovered clues in the most unexpected places, and the discoveries that reshaped how we see this planet. Are you ready? Before we can unravel the mystery, we need to travel back to the year 1815, when a Swiss carpenter accidentally stumbled upon a truth that humanity had overlooked for thousands of years. Jean-Pierre Perraudin was not a scientist. He was simply a carpenter who made a living guiding travelers across the Alps. Each day he walked the same familiar paths through narrow valleys and up steep mountain slopes. It was simple work, nothing remarkable. Until one day, he paused and looked at the enormous boulders scattered across the valley floor. These rocks had been there for as long as anyone could remember, long before he was born. People were used to them. No one paid them any attention. But Perraudin began to wonder, why were house-sized boulders sitting in the middle of the valley? Where had they come from? He looked around. The valley was made of limestone, a pale gray rock that is relatively soft, yet the giant boulders were granite, dark and incredibly hard. Granite did not exist here. The nearest source was high up on the mountain, dozens of kilometers away. So how did they end up down here? Floods? Impossible. No flood could be powerful enough to carry rocks weighing tens of tons. Earthquakes? That did not make sense either. Earthquakes can make rocks fall, but they do not drag them sideways for dozens of kilometers. Perraudin kept observing. He noticed long scratches carved into the bedrock beneath his feet. The grooves ran parallel to one another, strangely regular, as if something extremely heavy and unimaginably hard had scraped across the surface for a very long time. All the marks pointed in the same direction, from the high mountains down into the valley. Then it clicked. Glaciers, the massive rivers of ice flowing through the Alps. They move incredibly slowly, only a few meters each year, but they possess tremendous force. Ice can carry stones, it can grind and scratch the rock below. Perraudin began to believe that these glaciers must once have been far larger than they are today, spreading across the valleys, transporting granite boulders from the mountaintops and leaving them behind as the ice melted. He shared this idea with an engineer named Ignaz Venetz. Venetz laughed. Everyone laughed. The notion sounded absurd. Glaciers creep along like turtles. How could they possibly carry boulders the size of houses? How could they cover entire valleys stretching for kilometers? But Perraudin refused to give up. He took Venetz to see the scratches. He showed him how the boulders formed long lines like the traces of an immense flow. He spoke with mountain villagers whose families had lived there for generations. They all said the same thing. The glaciers used to be much larger. You could see the boundary where the ice once ended. You could see the piles of rocks the ice had left behind. Slowly, Venetz began to believe. He measured the grooves. He studied the boulders. He compared them with present-day glaciers. Everything fit together. In the year 1821, Venetz presented his findings to the Swiss Society of Natural Sciences. Most of the scientists dismissed the idea. Only a few were willing to listen.
There was one man who didn't laugh. His name was Louis Agassiz, a young geologist. Agassiz first heard about Venetz's theory through conversations circulating in scientific circles. At first, he was just as skeptical as everyone else. He thought Venetz must have been mistaken. There had to be a more reasonable explanation. In the summer of 1836, Agassiz set out for the Alps. His goal was to gather evidence that would once and for all disprove what he considered a ridiculous theory. He brought measuring instruments, notebooks, and a firm determination to show that glaciers could not possibly have done the things Venetz and Perraudin claimed. But the more he observed, the more he began to doubt his original beliefs. He saw granite boulders lying dozens of kilometers from where they had formed. He noticed deep scratches carved into the bedrock, marks that could only have been made by ice pressing down with immense force over long periods of time. He measured the movement of existing glaciers and found that they were indeed moving, slowly but relentlessly. Agassiz started to look beyond the Alps. These signs were not confined to one region. He read reports from Scotland, from Scandinavia, from many other parts of Europe. Everywhere there were strange, erratic boulders, similar scratch patterns, and the distinctive U-shaped alleys that only ice could create. In August of 1836, as summer drew to a close, Agassiz returned from the mountains with an entirely new conviction. He believed Venetz had been right, and more than that. Glaciers had not merely been a little larger in the past, they had once covered nearly all of northern Europe. Ice had spread southward from the Arctic, blanketing Scandinavia, crossing the North Sea into Britain, and extending into Germany, France, and Switzerland. Agassiz gave this phenomenon a German name, Eiszeit, meaning Ice Age. In July of 1837, he presented his theory at a major scientific conference. The reaction was not what he had hoped for. Most of the scientists present were upset, some even angry. The reason was simple. At the time, most scientists believed in catastrophism. They thought Earth's features were shaped by sudden, violent events. The most widely accepted explanation was the biblical Great Flood. They believed a massive deluge had once covered the entire planet. Waters rushed in with tremendous force, carrying rocks and boulders, carving scratches, then receded and left the landscape as we see it today. This theory seemed to explain many things, at least in their view. A boulder sitting in the middle of a valley, carried there by floodwaters, scratches on rock, gouged by debris in the rushing current, U-shaped valleys carved by erosion from flowing water. Agassiz was proposing something entirely different. He spoke of slow change unfolding over thousands of years, ice advancing gradually, only a few meters each year, yet never stopping. Nothing violent, nothing sudden, just time, an immense amount of time. This idea directly contradicted the prevailing beliefs of the era. But Agassiz had evidence. He took colleagues to see bedrock polished smooth. Floodwaters could not produce such surfaces. Only ice pressing down with enormous weight over long stretches of time could grind rock that way. He showed them parallel, orderly striations. Floods leave chaotic scratches with no consistent direction. Only ice moving steadily in one direction could create such patterns. He pointed out U-shaped valleys. Rivers carve V-shaped valleys, narrow and sharp at the bottom. Only vast, heavy glaciers can form U-shaped valleys with broad, flat floors. He showed them long ridges of debris called moraines, left along the sides as glaciers retreated. Floods do not leave behind deposits shaped like that. Slowly, very slowly, some scientists began to listen. Charles Lyell, the most influential geologist of the time, traveled to Scotland in 1840 to examine the evidence himself. He saw scratched rocks, erratic boulders, and glacial valleys. Everything matched what Agassiz had described. Lyell publicly supported the glacial theory. Once Lyell was convinced, many others began to follow. By 1850, the Ice Age theory had become the dominant view in the scientific community. Yet people still believed there had been only one Ice Age. Ice had covered the North once, then melted away, and that was the end of the story. But this was only the beginning. What they discovered next was far more unsettling, far stranger. Ice had not come just once and gone forever. It came, retreated, then came again, over and over, repeating like an endless cycle.
The 1860s marked a major turning point in our understanding of ice ages. Geologists began digging deeper, looking more closely. What they found left everyone stunned. Across many different places, from Scotland to Switzerland, from Germany to Scandinavia, they discovered a strange pattern in the ground and rocks. Not a single layer of glacial sediment as people had assumed, but multiple layers, interwoven with one another. The first layer was glacial sediment, crushed rock, gravel mixed with soil, chaotic and unstructured, the clear signature of ice. But above that lay a brown layer of earth, filled with roots, decaying leaves, clear signs that plants had once lived there. This meant that after the ice melted, the land had warmed enough for vegetation to return, forests to grow, animals to thrive. Yet above that soil sat another layer of glacial sediment. The ice had come back. After a warm period, it advanced again, covering the land and burying the forests. Then another soil layer, then glacial sediment again, layer upon layer, repeating over and over. James Geekie, a Scottish geologist, spent many years studying this phenomenon. He traveled across Scotland, digging deep pits, examining each layer carefully. He counted at least 4 distinct glacial deposits, each separated by soil layers bearing traces of life. 4 advances of ice, 4 retreats, 4 separate ice ages. He published these findings in the 1870s. Once again, the scientific world was astonished. Not one ice age, not 2, but many, perhaps dozens. Earth had not simply frozen once and then warmed forever. It froze, thawed, then froze again, then thawed again, in a repeating cycle. Similar evidence began appearing everywhere. In the Alps, geologists found multiple layers of glacial deposits stacked atop one another. Each time the ice advanced, it pushed rocks and soil forward, forming long ridges of moraine. Each time it retreated, it left those ridges behind. You could count the number of advances by counting the moraines. In North America, the evidence was even clearer. The Great Lakes region revealed layer upon layer of glacial deposits. Some were very old, heavily weathered, others newer, still fresh. Geologists realized that different ice sheets had advanced to different distances. During some ice ages, the ice pushed as far south as Missouri. In others, it stopped in Wisconsin. This raised an enormous question. Why? Why did the ice advance and retreat so many times? Not advance once and be done, or retreat once and stop. What was driving this cycle to repeat again and again? The biggest problem scientists faced at the end of the 19th century was time. How could they tell when these ice ages had happened? How could they measure the age of rock layers that were hundreds of thousands, even millions of years old? Back then, methods for dating rocks were still extremely crude. You could make rough estimates based on depth or the degree of weathering, but in the end, they were little more than educated guesses. There was no precise way to know. Radiocarbon dating would not be invented until the 1940s, and even that method works only for organic materials and only up to about 50,000 years. Scientists knew there had been multiple ice ages, but they did not know exactly how many, how long each one lasted, or how far apart they were. They needed a new way to peer into the distant past. The turning point came from a place no one expected: the ocean floor. In the 1950s, oceanographers began developing technology to drill deep into the seabed. They lowered long drill pipes thousands of meters beneath the surface, boring through layers of seafloor mud and pulling up sediment cores several meters long, sometimes even dozens of meters. These sediment cores held history. Each layer corresponded to a stretch of time. The top layer represented the present. The deeper you went, the farther back in time you traveled. It was like reading a book, each page a moment from the past. But the real magic lay in tiny organisms called foraminifera, often shortened to forams. Forams are single-celled creatures that live in the ocean. They build shells made of calcium carbonate. When they die, their shells sink to the seafloor and accumulate as sediment. Over millions of years, layer upon layer builds up, forming a continuous record of ocean history. What makes them so valuable is that their shells contain oxygen isotopes. Oxygen comes in different isotopic forms, with the two most important being oxygen-16, which is lighter, and oxygen-18, which is heavier. The ratio between these two in foram shells depends on the temperature of the seawater when they were alive. When the climate is cold, water evaporates from the ocean into the atmosphere. Water containing the lighter oxygen-16 evaporates more easily. This vapor falls near the poles as snow and accumulates into ice. The ice locks away oxygen-16, leaving the ocean relatively richer in oxygen-18. Forams living in this water form shells with higher oxygen-18. When the climate warms, ice melts and water rich in oxygen-16 flows back into the ocean. The proportion of oxygen-18 in seawater decreases. Forams living during these times form shells with less oxygen-18. By measuring the amount of oxygen-18 in foram shells from different sediment layers, scientists can reconstruct ocean temperatures at specific moments in the past. Ocean temperature reflects global climate. Cold means an ice age, warm means an interglacial period. In the 1960s and 1970s, scientists analyzed hundreds of sediment cores from around the world. They measured oxygen-18 ratios layer by layer. They plotted graphs with time along the horizontal axis and oxygen-18 along the vertical axis. The results astonished them. The graphs revealed a clear wave pattern, rising and falling again and again. Each peak represented an ice age. Each trough represented a warm period, not just 4 ice ages like James Geikie had counted in Scotland, but dozens. In just the past 2 million years alone, there had been at least 50 ice ages. Even more remarkable was how regular the cycles appeared. Ice ages did not occur at random, they followed a rhythm. Looking at the graphs, you could see that major ice ages occurred roughly every 100,000 years. Between the major cycles were smaller ones, spaced about 41,000 or 23,000 years apart. The data was there, the pattern was clear, but the biggest question remained: why? What creates this 100,000-year cycle? What controls the rhythm of the ice ages? This is where we need to meet a Serbian mathematical genius who spent years sitting in a library searching for the answer. At the dawn of the 20th century, once scientists were certain that ice ages occurred in cycles, they began proposing dozens of theories to explain why. Some sounded reasonable, others completely outlandish. One idea suggested that the sun's brightness changes over time, that it might shine more intensely for a while, then dim, then brighten again. When the sun dims, Earth cools and an ice age begins. When it brightens, the ice melts. It sounds plausible, but there is no evidence that the sun varies in brightness on a 100,000-year cycle. Another proposal argued that Earth passes through clouds of cosmic dust. As we move through these dusty regions, the particles block sunlight and cool the planet. Once we emerge, sunlight returns and the climate warms. This theory also fell apart because no one has found such dust clouds, and it fails to explain the regular timing. A different idea focused on volcanoes. Perhaps there were periods when volcanic eruptions intensified across the globe, filling the atmosphere with ash that blocked sunlight and cooled Earth. When eruptions subsided, the atmosphere would clear and temperatures would rise again. But there is no evidence that volcanic activity follows a steady cycle either. Some scientists believed changes in ocean currents were responsible. The oceans carry vast streams of warm water from the equator toward the poles and cold water back toward the equator. If these currents shifted or slowed, the climate would change dramatically. There is some truth here, yet it does not explain why such changes would happen on a regular schedule. There were even suggestions that Earth occasionally collides with large asteroids, the impacts throwing enormous amounts of dust into the atmosphere, blocking the sun and triggering ice ages. But asteroid impacts are random, not cyclical, so this idea was dismissed as well. All of these theories shared a common flaw. None could account for the strangely regular 100,000-year rhythm. Ice ages do not occur at random. They arrive with a clear cadence, almost like clockwork. There had to be a mechanism that was extraordinarily precise, extraordinarily dependable. The final answer came from someone who was not a climate expert, not a geologist. He was a mathematician, a civil engineer, a man who spent much of his life calculating numbers that few others cared about.
In 1912, Milutin Milankovitch was an engineering professor in Belgrade, Serbia. He taught about concrete structures, how to build bridges, how to calculate the strength of materials. The work was stable, but a little dull. He longed for a bigger challenge, a truly difficult problem. At a dinner with friends, someone mentioned ice ages. How could we know when the ice would come? The question stuck with Milankovitch. He began reading everything he could about climate, about glaciers, about the existing theories. He realized they all lacked one thing: precise mathematics. Milankovitch decided to approach the problem in a completely different way. He did not look for changes on Earth like volcanoes or cosmic dust. Instead, he looked at Earth's own motion around the sun. He knew Earth's orbit was not perfect. It changes over time. He wondered, could these changes be large enough to cause ice ages? He began calculating. The work was extraordinarily complex. There were no computers at the time. Every calculation had to be done by hand. Milankovitch sat in the library, day after day, working out Earth's position in space across hundreds of thousands of years. He calculated three main types of motion. The first was the shape of the orbit. Earth travels around the sun in an elliptical path, like a slightly flattened egg, but the degree of flattening changes over time. Sometimes the orbit is nearly a perfect circle, and Earth stays at a fairly even distance from the sun throughout the year. At other times, the orbit becomes more stretched, with Earth closer to the sun at one part of the year and farther away at another. This cycle lasts about 100,000 years. From a nearly circular orbit, it takes 50,000 years to reach its most elongated shape, then another 50,000 years to return to near circular. The number 100,000 years immediately caught Milankovitch's attention. That is the main Ice Age cycle. But there was a problem. Changes in orbital shape only alter the total sunlight Earth receives by a tiny amount, about 0.2%. That is far too small to trigger an ice age. Something else had to be involved. The second motion is the tilt of Earth's axis. Earth does not spin upright. It is tilted relative to the plane of its orbit. Today, the tilt is about 23.5 degrees, but this angle also changes over time, from 22.1 degrees to 24.5 degrees and back again. This cycle lasts about 41,000 years. When the tilt is greater, the difference between summer and winter becomes more extreme. Summers are hotter, winters are colder. When the tilt is smaller, the seasons are milder. Summers are cooler, winters are warmer. Milankovitch realized something crucial. Ice ages do not happen when winters are extremely cold. They happen when summers are extremely cool. Why? Because snowfall in winter is always there. The question is whether it melts completely in summer.
If summers are cool, the snow does not fully melt. It accumulates year after year, gradually turning into ice. So, when Earth's tilt is smaller, summers are cooler, snow builds up, ice begins. When the tilt is larger, summers are hotter, snow melts away, the ice retreats. The third motion is the wobble of Earth's axis, called precession. Earth spins like a slowing top. Its axis does not just point in one direction, it slowly traces a circle, like the head of a spinning top as it begins to wobble. One full wobble takes about 23,000 years. This changes the time of year when Earth is closest to the Sun. Today, Earth is closest in January, during winter in the Northern Hemisphere. But 11,000 years ago, Earth was closest in July, during Northern Hemisphere summer. This has major consequences. When Earth is closest to the Sun in summer, summers become hotter, more snow melts. When Earth is farthest from the Sun in summer, summers are cooler, less snow melts, making it easier for ice to accumulate. Milankovitch spent years calculating how these three motions interact. He calculated how much sunlight reaches each latitude on Earth on every day of the year across the past 600,000 years. It was a monumental task, thousands of calculations, hundreds of pages of numbers. In 1920, he published his results. He drew charts showing how solar radiation changes over time. He pointed out periods when all three cycles align, producing extremely cool summers in the Northern Hemisphere, times when ice begins to grow, and periods when the cycles combine to produce extremely hot summers when ice melts. He compared his charts with geological evidence of past ice ages. The match was astonishing. His theory accurately predicted when ice advanced and when it retreated. But there was a tragedy. Milankovitch published his theory at a very unfortunate time. The world was going through the First World War, then the Second World War. Scientists were busy with war and reconstruction. Few had time to study ice ages. And his theory was extremely complex, filled with mathematics. Many simply did not understand it. Milankovitch died in 1958 at the age of 79. He died disappointed, believing his life's work had been forgotten. But he was wrong. Just 10 years after his death, scientists began obtaining data from the ocean floor, records of oxygen-18 ratios spanning millions of years. In 1976, a group of scientists published a groundbreaking study. They compared ocean sediment core data with Milankovitch's calculations. The agreement was nearly perfect. The peaks and valleys in the oxygen-18 record lined up precisely with the times Milankovitch predicted for ice ages or warm periods. In particular, they found a clear 100,000-year cycle, exactly as he had calculated. The 41,000-year and 23,000-year cycles were also present, all visible in the data. Milankovitch's theory was confirmed. The scientific community erupted with excitement. At last, after more than a century of searching, they had an answer. Ice ages occur because Earth's orbit changes, not because of the Sun. Not because of volcanoes, not because of cosmic dust, but because Earth itself dances through space, tilting back and forth, wobbling like a spinning top, circling the Sun along ever-shifting paths. Milankovitch had been right all along, but he did not live to see his victory. It remains one of the great tragedies in science. A genius devotes his life to a problem, finds the correct answer, yet no one believes him until after he is gone. It is a sad story, but also an inspiring one. It shows that perseverance matters. It shows that truth is eventually recognized, no matter how long it takes. Today, Milankovitch theory forms the foundation of paleoclimate science. Yet there is a problem, a serious problem that still puzzles scientists today. Milankovitch theory explains when ice ages occur, but not why they become so massive. The changes in sunlight he calculated are tiny, yet the actual ice ages involve enormous transformations. Something must amplify the signal. What is that amplifier?
Milankovitch theory looks perfect on paper. The numbers line up, the cycles are clear, but when scientists began running more detailed calculations, they uncovered a major problem. The changes in sunlight that Milankovitch calculated are actually very small.
When Earth's orbit shifts from nearly circular to more elliptical, the total amount of sunlight changes by only about 0.2%. When Earth's tilt increases or decreases, summer sunlight at high latitudes changes by around 10%. That may sound significant, but it only affects certain regions and only for short periods. Scientists estimate that these variations are enough to change global temperatures by roughly 1 to 2 degrees Celsius. Some regions might warm a bit more, others a bit less, but on average, that is the scale of the effect. The problem is real ice ages are not a 1 to 2 degree story. During glacial periods, global temperatures fall by 5 to 10 degrees Celsius, sometimes even more in certain places. In Northern Europe, temperatures dropped by as much as 20 to 25 degrees Celsius. In North America, areas that now enjoyed temperate climates became as cold as the Arctic. Sea levels fell by 120 meters. Ice sheets spread across tens of millions of square kilometers. Entire ecosystems were reshaped. The Sahara expanded, tropical forests shrank, giant animals appeared and later vanished. How could a modest shift of 1 to 2 degrees trigger consequences on the order of 5 to 10 degrees? There must be some mechanism that amplifies the signal. Like nudging a small stone down a slope, it begins to roll, gathering other rocks along the way until it becomes a massive avalanche. The initial push is small, but the final outcome is enormous. The million-dollar question is, how does this amplifier work? What transforms a subtle change into a planet-wide surge of ice?
The answer lies in a concept scientists call positive feedback. It sounds technical, but the idea is very simple. Positive feedback happens when a small change creates an effect. That effect triggers more change in the same direction, making the original change bigger, then bigger still, growing step by step. It is like standing near a microphone connected to speakers. A tiny sound goes into the microphone, the speakers play it back, the sound re-enters the microphone, comes out louder, then louder again, until you hear that piercing screech. That is positive feedback. Earth has many positive feedback mechanisms. They intertwine, amplifying one another, turning small causes into enormous changes. The first mechanism, and the easiest to understand, is the reflectivity of ice and snow. Scientists call this the albedo effect. Albedo is a surface's ability to reflect light. The lighter the surface, the higher the albedo and the more light it reflects. The darker the surface, the lower the albedo and the more light it absorbs. Fresh white snow has a very high albedo, about 80 to 90%. That means snow reflects 80 to 90% of incoming sunlight, absorbing only 10 to 20%. Ocean water has a very low albedo, only about 6%. It absorbs 94% of sunlight and reflects just 6%. Bare ground and forests have albedo values ranging from 10% to 30%, depending on the surface. Now, imagine what happens when the climate cools slightly because of changes in Earth's orbit. Summers become a little cooler. Snow in the polar regions and on high mountains does not fully melt. A thin layer of snow survives through the summer. Winter arrives, new snow falls on top of the old. The snowpack thickens. The next summer, it still does not completely melt. Year after year, snow accumulates, compacts, and gradually turns into ice. The bright surface of snow and ice reflects more sunlight back into space. Reflected light does not bring heat into the Earth system. The region grows colder. Colder means more snow means more reflection means even colder conditions. This is a loop. Cold creates snow creates reflection creates cold creates more snow. The loop does not stop, it reinforces itself. From a thin layer of snow, you can end up with vast sheets of ice. Ice begins to spread. From the poles, it advances southward. With every meter of ice that moves forward, another meter of bright surface reflects sunlight.
Nearby regions cool, snowfall increases, the ice advances further, and so it continues. At the peak of the ice ages, ice covered Canada, blanketed Scandinavia, stretched down into Britain, into Germany, and across the northern United States. Tens of millions of square kilometers of bright surface reflected sunlight. Earth looked brighter from space, yet far colder. Then Earth's orbit shifts the other way. Summers grow a little warmer. Ice at the margins begins to melt. Meltwater flows away, exposing darker soil and rock beneath. Dark surfaces absorb more heat. The region warms. As it warms, more ice melts. More melting exposes more ground. More ground absorbs more heat. More absorption leads to more warming. Another loop forms, but in reverse. Warmth causes melting, melting reveals land, land absorbs heat, heat brings more warmth causes more melting. The ice retreats toward the poles. This mechanism alone can amplify the signal by about 2 to 3 times. A change of 1 degree Celsius can become 2 or 3 degrees. But it is still not enough to explain the full scale of ice ages. Other mechanisms must also be at work.
The second mechanism involves carbon dioxide, or CO2. You've probably heard of CO2 as a greenhouse gas, and that's exactly what it is. CO2 in the atmosphere acts like a blanket, trapping heat and preventing it from escaping into space. The more CO2 there is, the warmer Earth becomes. The less CO2, the colder it gets. What's remarkable is that the concentration of CO2 in the atmosphere also shifts with the rhythm of the ice ages. During glacial periods, CO2 levels drop. During warmer intervals, they rise. So who controls CO2? The answer is the oceans. The oceans are a massive reservoir of CO2. Seawater absorbs CO2 from the atmosphere, and how much it can hold depends on temperature. Cold water dissolves CO2 far more effectively than warm water, much like a chilled soda holds onto its fizz longer than one left out in the heat. As the climate begins to cool, the oceans cool as well. Colder water absorbs more CO2, pulling it down from the atmosphere. Atmospheric CO2 levels fall. With less CO2, the greenhouse effect weakens. A weaker greenhouse effect allows more heat to escape into space, and the planet cools even further. As it gets colder, the oceans cool more. Cooler oceans absorb additional CO2. More absorption means less CO2 in the air, and less CO2 means more cooling. It becomes a self-reinforcing loop. At the peak of an ice age, atmospheric CO2 concentrations fall from about 280 parts per million to around 180 parts per million, a drop of nearly 40%. The greenhouse effect weakens significantly, making Earth even colder, by roughly 2 to 3 degrees Celsius from CO2 alone. Then, as Earth's orbit shifts, the climate begins to warm. The oceans warm too. Warm water cannot hold as much CO2, so the gas starts to escape from the oceans back into the atmosphere, like opening a bottle of soda left in the sun and watching the bubbles rush out. More CO2 in the atmosphere strengthens the greenhouse effect. Earth retains heat more efficiently, becoming warmer. As temperatures rise, the oceans warm further. Warmer oceans release even more CO2, and with more CO2 comes additional warming, another feedback loop in motion. How do we know all this? From ice cores in Antarctica. Scientists have drilled deep into the Antarctic ice sheet, extracting cylinders of ice stretching for miles. This ice formed from snow that fell thousands of years ago and was gradually compressed. Trapped within it are tiny bubbles of ancient air, sealed at the moment the snow first settled. By analyzing these bubbles, scientists can measure the concentration of CO2 in each one. Every bubble represents a snapshot in time. The longest ice cores allow researchers to track atmospheric CO2 over the past 800,000 years. The results are striking. The CO2 record aligns almost perfectly with temperature records. When temperatures rise, CO2 rises. When temperatures fall, CO2 falls. Same cycles, same rhythm, rising and falling together. There is one subtle but crucial detail.
Scientists have found that temperature changes occur slightly before CO2 shifts. In other words, changes in Earth's orbit initiate temperature changes. Those temperature changes alter CO2 levels, and then CO2 amplifies the temperature changes. Everything is connected. The third mechanism is more complex, involving the flow of the oceans. The ocean is not a motionless body of water. It is threaded with immense currents, like rivers within the sea, carrying water from the equator toward the poles and from the poles back toward the equator. The most important of these is called the thermohaline circulation. The name sounds technical, but the idea is simple. Warm water from the tropics flows northward along the surface, carrying heat with it. When it reaches the North Atlantic near Greenland, the water cools, and evaporation makes it saltier. Cold, salty water is denser than warm, fresher water, so it sinks to the ocean floor. This sinking creates a deep current that flows back southward. It travels along the seabed, circles Antarctica, then rises through the Pacific and Indian Oceans, where it warms and returns to the surface before eventually flowing back into the Atlantic. One full loop takes about 1,000 years. This circulation acts like a conveyor belt for heat, transporting heat from the equator to the far north. Because of it, northern Europe is much warmer than regions at the same latitude in North America. London sits at roughly the same latitude as Calgary in Canada, yet it is far milder thanks to the warm ocean current. The problem is that this circulation is extremely sensitive. It depends on differences in water density. The water must be cold enough and salty enough to sink. If too much fresh water pours into the North Atlantic, the water becomes diluted, lighter, and no longer sinks as it should. What produces this fresh water? Melting. Ice in Greenland or ice on land melts. Fresh water flows into the sea. If enough fresh water accumulates, the circulation can slow down or even stop entirely. When the circulation stops, northern Europe no longer receives heat from the tropics. The climate there becomes much colder, potentially dropping by 10 to 15 degrees Celsius. Colder conditions mean more ice. Ice sheets grow, glaciers expand. Even more intriguingly, this circulation also affects carbon dioxide. When the current operates normally, it brings carbon dioxide-rich water from the deep ocean to the surface, releasing carbon dioxide into the atmosphere. When the current stops, carbon dioxide remains trapped in the depths, unable to escape. Atmospheric carbon dioxide levels fall, and the Earth cools even further. Conversely, when an ice age ends, rapid melting sends large amounts of fresh water into the ocean. The circulation may shut down temporarily, but once the ice is gone and the fresh water supply diminishes, the ocean becomes salty again and the circulation restarts. When it switches back on, it carries heat northward, leading to rapid warming. Ocean currents behave like an on-off switch. When they are on, the climate is warm. When they are off, the climate is cold. And this switch can flip surprisingly quickly, sometimes within just a few years or a few decades. The final mechanism, perhaps the least expected of all, involves desert dust, tiny drifting life in the ocean, and a humble element called iron. Phytoplankton are microscopic organisms that float near the ocean's surface. Like plants on land, they photosynthesize, drawing carbon dioxide from seawater and using sunlight to produce energy. When they die, they sink to the seafloor, carrying the carbon dioxide they absorbed with them. That carbon becomes buried in sediments, locked away instead of returning to the atmosphere. Phytoplankton need nutrients to grow, and one of the most crucial is iron. But iron is extremely scarce in the open ocean. Most of it is trapped in rocks on land, leaving phytoplankton limited by this shortage, unable to flourish as much as they otherwise could. When the climate cools, deserts expand. During ice ages, the Sahara was more than twice its current size. Winds sweeping across these vast dry regions pick up fine dust and carry it far out over the sea where it settles onto the surface waters. That dust contains iron. Iron delivered by desert dust fertilizes the phytoplankton. They bloom. As they grow, they pull more carbon dioxide out of the atmosphere. Atmospheric carbon dioxide drops and the planet cools further. A colder world allows deserts to expand even more. Larger deserts produce more dust. More dust brings more iron. More iron feeds more phytoplankton. More phytoplankton draw down more carbon dioxide. Another feedback loop closes. It may sound far-fetched, yet scientists have uncovered evidence in Antarctic ice cores. The ice preserves dust carried from across the globe. By counting the amount of dust in each layer, researchers found that during ice ages, dust levels rose many times over, while in warmer periods they declined. They have also measured iron concentrations in ocean sediments. Ice age layers contain more iron. Counts of fossilized phytoplankton show higher abundances during those same cold periods. The lines of evidence all align. None of these mechanisms, albedo, carbon dioxide, ocean circulation, desert dust, operates in isolation. They intertwine and amplify one another, like a symphony orchestra where each instrument plays its part, yet together they create something vast and powerful. Earth's orbit shifts slightly, setting change in motion. Expanding ice reflects more sunlight, doubling the effect. Carbon dioxide falls, amplifying it again. Ocean currents reorganize, adding further momentum. Desert dust spreads, strengthening the shift even more. Taken together, a small change of 1 degree Celsius can grow into 5, 10, or even 15 degrees in some regions. This is the answer to the Milankovitch paradox. He was right about the cycles and their timing, but he did not know the amplifying mechanisms behind them. Earth is not a passive system that simply receives sunlight and responds in proportion. It is a dynamic world, filled with feedback loops that reinforce and regulate themselves. That is both wondrous and unsettling. Wondrous because it reveals how intricate and finely tuned this planet truly is. Unsettling because it shows how sensitive the system can be to small disturbances. A gentle push can lead to enormous consequences. And this brings us to the mysteries that remain only partly understood, the strange questions scientists are still debating today.
You might think everything is already clear. Milankovitch identified the cycles, scientists uncovered the amplification mechanisms, case closed. But listen to this. There is a major paradox that still has not been satisfactorily explained. The orbital eccentricity cycle lasts about 100,000 years, exactly the same length as the major ice age cycle, a perfect match. The problem is that this orbital cycle is actually the weakest of the 3 cycles Milankovitch calculated. The shift from a more circular orbit to a more elliptical one changes the total amount of sunlight Earth receives by only about 0.2%. Meanwhile, the 41,000-year tilt cycle alters summer sunlight at high latitudes by as much as 10%. The 23,000-year wobble cycle produces changes far greater than those caused by orbital eccentricity. In theory, the 41,000-year and 23,000-year cycles should dominate. Ice ages should mainly follow those rhythms, but that is not what we see. Over the past 2 million years, especially during the last 1 million years, the 100,000-year cycle overwhelmingly takes the lead. Look at temperature records from sediment cores and it becomes obvious. Major glacial periods are spaced roughly 100,000 years apart. Between them are smaller fluctuations, likely tied to the 41,000 and 23,000 year cycles, but they appear like small ripples riding on top of much larger waves. The big wave is 100,000 years. Why does the weakest cycle dominate? This question has puzzled scientists for decades. Many ideas have been proposed. Some suggest a resonance effect, like pushing a swing. If you push at just the right rhythm, even a gentle force can send the swing soaring. Perhaps the smaller cycles resonate with each other in some way, producing the large 100,000-year rhythm. Others argue that the massive ice sheets covering North America and Northern Europe play a special role. Ice does not respond instantly to climate changes. It has inertia. Once an ice sheet grows large, it is hard to melt. It takes a great deal of heat to erode ice that is miles thick. It may be that ice responds only weakly to the 23,000 and 41,000 year cycles, but strongly to the 100,000 year cycle,
because that span is long enough for ice to fully accumulate and then fully retreat, like a giant pendulum swinging slowly but with great force. Another idea involves thresholds. The climate system may have tipping points. When temperatures fall below a certain level, ice begins to build rapidly. When they rise above another, ice melts quickly. The 100,000-year cycle might be the only rhythm strong enough to push the system across these thresholds. Scientists have built extraordinarily complex computer models, simulating Earth's climate over millions of years. They feed in the Milankovitch cycles and feedback processes, trying to reproduce real-world data. Some models come close, but none are perfect. The challenge is that Earth is incredibly complex. Too many factors interact: ice, water, atmosphere, living systems, oceans, all influencing one another in ways we still do not fully understand. The mathematics becomes extremely difficult. Even with supercomputers, we still do not have a complete answer. It is a reminder that despite all our progress, there is still much to learn. Earth continues to hold its secrets, and the mystery of the 100,000-year cycle remains one of the greatest of them.
There were also moments when the script went off track, strange exceptions no one saw coming. The most famous story is the Younger Dryas, named after a tiny flower that thrives in cold climates. This episode unfolded around 12,800 years ago. At that time, the last ice age was coming to an end. About half the ice had already melted. Global temperatures had risen significantly. Forests were beginning to return to lands once buried under ice. Everything seemed to be moving in the right direction, toward a fully warm world. Then suddenly, over just a few years to a few decades, temperatures plunged again. Not by a little, but dramatically, almost back to Ice Age conditions. Northern Europe and North America froze once more. The melting stopped, even reversing slightly. Plants died off, animals migrated or vanished. This cold phase lasted roughly 1,000 years, from 12,800 to 11,700 before the Common Era, more than a millennium locked in ice. Then, just as abruptly as it began, temperatures shot back up. Within a decade or two, Greenland warmed by 10 degrees Celsius. Ice melted quickly, warm conditions returned. The Younger Dryas was like a sudden jolt in the middle of sleep. The Ice Age was ending smoothly, then it snapped back, and then it ended again. Why? Scientists spent many years searching for the answer. The likely cause was a colossal glacial lake in North America. As the ice melted, water pooled into vast lakes on top of the ice or trapped between ice sheets. One of them, Lake Agassiz, was larger than all the Great Lakes combined, a massive body of cold, fresh water held back by ice dams. Around 12,800 years ago, the ice dam failed, perhaps from cracking, perhaps because water levels rose too high. An enormous volume of fresh water, thousands of cubic kilometers, surged into the North Atlantic over a very short time, possibly just months or a few years. Fresh water is lighter than salt water, so it formed a floating layer across the North Atlantic. This lighter layer prevented cold, salty water from sinking. The thermohaline circulation, the great global heat conveyor we talked about earlier, stalled. Without that circulation, Northern Europe no longer received heat from the tropics. Temperatures there dropped sharply. Ice began to grow again. The global climate cooled. The Younger Dryas had begun. After more than 1,000 years, the fresh water gradually mixed back into the ocean or dispersed elsewhere. The sea became salty again, circulation restarted, heat flowed north once more. The Younger Dryas ended as quickly as it had started. This story shows just how sensitive the climate system is. A single event, a lake bursting through its icy barrier, was enough to disrupt the global climate for over 1,000 years. The system has switches, and when they flip, everything can change very fast. The Younger Dryas was not the only exception. Scientists have found evidence of many similar events in the past. There was an episode about 8,200 years ago known as the 8.2 kiloyear event.
Again, a glacial lake drained. Again, fresh water poured into the North Atlantic. Again, circulation slowed. Again, the climate cooled abruptly. This time it lasted only about 400 years, but still caused major impacts. There are also events called Heinrich events, named after the scientist who identified them. These were periods during ice ages when enormous armadas of icebergs broke off from the ice sheets in North America or Northern Europe, drifted into the North Atlantic, melted, released fresh water, and disrupted ocean circulation. They occurred multiple times during the last ice age, each bringing powerful climate swings. These exceptions remind us that even though we understand a great deal, much remains unknown. The climate system is not perfectly smooth, not perfectly predictable. It holds surprises, sudden jolts, abrupt shifts no one expects. What is unsettling is that such exceptions can happen at any time. Today, Greenland's ice is melting. The flow of fresh water into the North Atlantic is increasing. Is it enough to slow the circulation? Could another younger Dryas happen in the future? Scientists are watching closely. They measure the strength of the circulation, track freshwater inputs, and try to anticipate what might come next. But prediction is difficult. The system is extraordinarily complex, with too many variables. These strange exceptions also remind us of something important. History does not repeat itself exactly. Each ice age is slightly different. Each warm period has its own character. There's a broad pattern, but the details always shift. Earth is like a jazz musician, playing within a familiar theme but improvising differently each time. That makes predicting the future far more challenging. We understand the general trends and the major cycles, yet we cannot know precisely how every detail will unfold, especially now that a new factor has entered the story, something unseen for millions of years: humanity.
Now let's turn back the clock. Forget the world as it is today. Forget the cities, the cars, the phones. Go back 20,000 years to the peak of the last ice age. That world is completely different from ours. Stand on the coastline where New York City now sits, and you wouldn't see water. You'd be standing on a field of dry grass, cold winds sweeping across the land. Behind you, to the north, rises a towering white wall: ice. A sheet of ice more than 2 kilometers thick, higher than any skyscraper humans would one day build. It stretches as far as the eye can see, from east to west, from the Atlantic to the Pacific, covering all of Canada and the northern half of the United States. Sea levels are about 120 meters lower than today. Water has turned to ice, locked away at the poles, across North America, in Northern Europe, and atop mountain ranges around the world. The oceans have shrunk. Continental shelves lie exposed. Places that are now deep sea were once dry land. You could walk from Siberia to Alaska. The Bering Strait is no longer a strait, but a vast land bridge stretching thousands of kilometers. We call it Beringia. A wide, wind-swept steppe, harsh and cold, yet full of life. Mammoths, wild horses, and musk oxen move in great herds. You could walk from Britain to France, to the Netherlands, to Germany. The North Sea is a low plain threaded with rivers and streams. People live there, hunting and fishing. Today it lies beneath the waves, but archaeologists still recover stone tools and human bones dredged from the seafloor. Indonesia, Malaysia, Thailand, and the Philippines are joined together into a single great landmass called Sundaland. No seas divide them. Animals move freely from region to region, and so do humans. The climate is far colder. Global average temperatures are about 5 to 6 degrees Celsius lower than today. It doesn't sound like much, but the consequences are enormous. Far from the equator, the difference can reach 15 to 20 degrees Celsius. Paris and London feel more like modern Siberia. Winters last 8 or 9 months. Summers are brief and cool, not warm enough to melt all the snow.
The Sahara Desert is twice its current size, spreading southward and covering regions that are now lush grasslands. The Amazon rainforest shrinks into scattered pockets. Much of the Amazon basin becomes dry savanna. The Congo rainforest contracts in a similar way. Yet this is not a dead world. It is alive, just alive in a different way. A world of giant creatures, animals we now only see in museums. Woolly mammoths stand up to 4 meters tall at the shoulder, with curved tusks reaching 5 meters long. They roam in herds across frozen plains, using their tusks to sweep away snow and uncover dry grasses beneath. Thick fur blankets their bodies, keeping them warm in temperatures of -40 degrees Celsius. Woolly rhinoceroses, as large as trucks, carry long, razor-sharp horns. They bellow as they defend their territory. Cave bears, larger than modern brown bears, hibernate deep in caves and awaken in summer to hunt. Cave lions, about 25% larger than African lions, lack manes and wear thick coats against the cold. They hunt in groups, stalking young mammoths or weakened muskoxen. Dire wolves, towering deer with antlers spanning up to 3.5 meters, giant ground sloths in South America, and enormous flightless birds in Australia. A world of powerful creatures built for the cold.
Amid that frozen world, our ancestors lived. They endured. They struggled against a brutal environment, yet they also grew, invented, and slowly became the kind of humans we are today. They lived in small bands, usually around 20 to 50 people, large enough to hunt effectively and protect one another, but not so large that food ran short. They moved constantly, following herds, following the seasons, searching for food, water, and shelter. Life was extraordinarily harsh. Winters stretched on for months, sometimes even for years. Temperatures plunged to -30, -40 degrees Celsius. Winds swept down from the northern ice sheets, cold enough to cut through skin and bone. Snow buried everything. Food was scarce. Many people, especially children and the elderly, did not survive the winter. And yet they were remarkably intelligent, deeply creative. They developed ingenious technologies to stay alive. Stone tools were their core technology. They knew how to shape flint and obsidian into blades as sharp as modern razors, spear points honed for hunting large animals, small knives for skinning and cutting meat, axes for chopping wood and splitting bones. Each tool was crafted with care, demanding skill and years of experience. They invented needles made from bone or ivory with tiny eyes for threading. The thread itself came from animal sinew, tough and durable. With needle and thread, they stitched clothing from animal hides, thick coats of reindeer or bear skin, long trousers, fur-lined boots, ear-covering hats, gloves, complete outfits designed to hold warmth against the terrifying cold. They built homes from the bones of mammoths. In regions without trees or stone for shelter, they gathered enormous mammoth bones, arranging them into dome-shaped frames, covering them with hides, piling earth on top for insulation. Fires burned inside. A family could survive the entire winter in such a dwelling. Fire was the most essential technology of all. Without it, survival was impossible. Fire provided warmth, cooked food, drove away predators, and lit the darkness. They knew how to drill wood to spark flames, how to strike flint to create sparks, how to keep embers alive. Fire sat at the center of life, people gathering around it to tell stories, share meals, and plan the hunt. They hunted giants. A single mammoth could feed an entire group for many weeks, but hunting one was dangerous and required strategy. They worked together, surrounding the animal and striking with spears again and again until it fell, or driving it toward cliffs and forcing it over the edge. Risky, but effective. They fished, dove for shellfish, dug for roots, gathered berries whenever they could, never ignoring any possible source of nourishment. In a harsh world, flexibility meant survival. But they did more than survive. They created art.
Deep inside caves in France and Spain, they painted stunning images of animals, horses, bison, deer, mammoths, rendered with charcoal, mineral pigments, even animal blood. Some paintings reached a level of sophistication rivaling that of modern artists. They carved small figures from bone, ivory, and stone, human forms, especially pregnant women, animal shapes as well. These objects may have carried spiritual meaning, served as charms for luck, or simply been expressions of creativity. They made musical instruments, flutes carved from bird or reindeer bones with carefully placed holes to produce melodies, drums made from stretched hides over frames. Perhaps they sang and danced around campfires, telling stories of hunts, of ancestors, of the world around them. They buried their dead with care and ceremony, laying bodies in graves alongside weapons, tools, and ornaments, sprinkling red ochre over them, perhaps symbolizing blood or life. This suggests beliefs in an afterlife, in spirits, in existence beyond death. They were not merely animals trying to survive, they were humans with inner worlds, with thoughts, with faith. Around 15,000 years ago, the ice began to melt. No one knew why. They only noticed warmer summers, more melting snow, retreating glaciers, new lands emerging. Some groups followed the receding ice northward into newly opened territories, hunting reindeer and salmon along fresh coastlines. Others crossed Beringia, the land bridge connecting Siberia and Alaska, entering the Americas, an entirely new continent to them. They spread from Alaska to California, through Mexico, into South America. Within a few thousand years, humans lived from the Arctic to the southern tip of the continent. Some stayed where they were, but adapted to a changing climate. Forests returned. The great megafauna gradually disappeared, replaced by smaller animals, deer, elk, wild boar. People learned new ways to hunt, new ways to live among trees instead of across frozen plains. Then, some groups, especially in the Middle East, began experimenting with something entirely new: agriculture. Instead of hunting and gathering, they cultivated barley and wheat, domesticated goats and sheep, settled in one place, built permanent homes. This marked the greatest turning point in human history. From agriculture came civilization, villages, cities, empires, cultures, all growing from that single shift. Our ancestors lived through the Ice Age. They did not merely endure, they thrived. They spread across the planet, creating art, technology, culture. We are their descendants. Each of us carries the genes of people who faced ice, hunger, endless winters, and still persisted. Would we, with all our modern technology, be able to do the same if the ice returned? Or have we grown too dependent on comfort, too distant from nature to endure? It is a question worth contemplating, but before we answer, we must look ahead, towards the future, towards what we ourselves are now creating.
200 years. Just 200 years. It sounds impossibly brief when you compare it to the 100,000-year rhythm of ice ages, when you place it beside the millions of years of Earth's history. And yet, in those 2 centuries, humanity has reshaped this planet in ways no other species ever has. In 1800, the world still ran much as it had for thousands of years. People burned wood for fire, traveled by horse-drawn carts, farmed by hand. Energy came from muscle, from the wind, from flowing water. The atmosphere held about 280 parts per million of carbon dioxide, roughly in line with previous warm periods. Then the Industrial Revolution began. Humans learned to mine coal and burn it to power machines. Coal is the compressed remains of plants that lived hundreds of millions of years ago, buried deep underground and transformed into carbon-rich black rock. When burned, the carbon in coal combines with oxygen in the air to form carbon dioxide, releasing energy. At first, there were steam engines, then textile mills and steel factories. Coal-powered trains, coal-powered ships. Cities glowed under gas lamps made from coal. Carbon dioxide from burning coal drifted into the atmosphere. By the late 19th century, humans discovered oil. Oil comes from ancient marine life, also rich in carbon like coal.
It is easier to transport and more energy-dense. The internal combustion engine was invented. Cars appeared. Airplanes took flight. Plastics were made from oil. Chemicals, fertilizers, pesticides, all derived from oil. In the 20th century, natural gas joined the story. Natural gas is another fossil carbon fuel. Together, coal, oil, and gas became the backbone of modern civilization. Every time we burn them, carbon dioxide is released. 200 years of continuous burning. Billions of tons of coal, oil, and gas turned into smoke. Carbon locked underground for millions of years has been released into the atmosphere in just 2 centuries. The result? Atmospheric carbon dioxide has risen from 280 parts per million to 420 parts per million, an increase of 50%. The rate of change is unprecedented in the past 800,000 years, perhaps in millions. During natural ice age cycles, carbon dioxide rose from about 180 to 280 parts per million over roughly 10,000 years. Humans have done more than that in just 200 years, about 50 times faster than natural rates. The consequences are clear. Carbon dioxide is a greenhouse gas. It traps heat that would otherwise escape to space. The more carbon dioxide, the warmer the planet. Global temperatures have risen by about 1.1 degrees Celsius since 1850. It may sound small, but that is a global average. In some regions, especially the Arctic, warming is 2 to 3 times greater. Ice is melting. Greenland loses roughly 280 billion tons of ice each year. Antarctica loses about 150 billion tons annually. Massive ice sheets fracture, drift into the ocean, and melt. Glaciers in the Alps, the Himalayas, the Andes, Alaska, and across the world are retreating. More than 90% of the world's glaciers are shrinking. Sea levels are rising, currently about 3 millimeters per year. It sounds minor, but over the past 100 years, sea level has risen roughly 20 centimeters, and the rate is accelerating. Rising seas come not only from melting ice, but also from warming water expanding and occupying more volume. The climate is shifting. Summers are hotter. Heat waves last longer. Storms grow more intense. Some regions see heavier rainfall, others face deeper drought. Seasons no longer behave as they once did. Snow falls later and melts earlier. Living things must adapt or move. Plants in temperate regions are creeping higher up mountains and spreading northward. Migratory birds are changing routes. Fish swim toward cooler waters. Some species cannot adapt quickly enough and face extinction. Humans feel the effects too. Farmers must change crops as local climates become less suitable. Coastal communities worry about rising seas. Major cities like Jakarta, Bangkok, Miami, and Venice face growing flood risks. Some small Pacific islands may disappear entirely. All of this has happened with just about 1.1 degrees of warming. We are heading toward 1.5 degrees in the coming years, possibly 2 degrees by mid-century if nothing changes. Every additional tenth of a degree brings greater consequences.
What happens next? Will the next ice age arrive, or have we broken the 100,000-year cycle forever? No one knows for sure, but scientists have outlined 3 possible scenarios. The first scenario, and the one many researchers consider most likely, is that the ice age cycle gets postponed. The idea is this: the carbon dioxide humans release is powerful enough to counteract the Milankovitch cycles. Earth's orbit will keep changing as it always has. The axis will keep tilting and wobbling, but the greenhouse effect from human-made carbon dioxide is far stronger than the cooling effect driven by orbital shifts. Scientists have run computer models. Their calculations suggest that with current carbon dioxide levels, the next ice age, which would have been expected to begin in about 10,000 to 15,000 years, could be delayed by another 50,000 to 100,000 years. If humanity continues burning fossil fuels at the current pace, or even accelerates, carbon dioxide levels could reach 600, 700, or even 1,000 parts per million. At those concentrations, the next ice age could be postponed for 500,000 years, or might not arrive at all while carbon dioxide remains high. It sounds like good news, doesn't it? Escaping an ice age, avoiding a frozen world, no need to worry about ice sheets covering cities.
But it isn't that simple. Earth's ecosystems have adapted to ice age cycles over the past 2 million years. Many species evolved to survive these rhythms. They migrate when the ice advances, return when it retreats. They shift their behavior, their size, their entire way of life to match the cycle. Breaking the cycle means disrupting that natural balance. Many species will not be able to adapt quickly enough. They will go extinct. Ecosystems could unravel. A world without ice ages for hundreds of thousands of years would look very different from one shaped by regular cycles. And if temperatures keep rising, it is not just about delaying an ice age. It means making Earth warmer than at any point in the past several million years. Ice in Greenland could completely melt. Ice in West Antarctica could collapse. Sea levels could rise 7 meters from Greenland, plus another 3 to 5 meters from Antarctica, adding up to 10 to 12 meters in total. Most coastal cities would be flooded. New York, London, Tokyo, Shanghai, Mumbai, Bangkok would all face relocation or the construction of massive sea defenses. Hundreds of millions of people would be forced to migrate. Agriculture would collapse in many regions because of extreme heat and drought. Conflicts over resources, over water, over land would intensify. Delaying an ice age might feel like escaping the frying pan, only to leap into the fire.
The second scenario, one that fewer people believe but is still possible, is that the ice age cycle continues as usual despite human-made carbon dioxide. The idea here is that human emissions are only a temporary disturbance. For a few hundred or a few thousand years, carbon dioxide levels may stay elevated. But over the long run, Earth has ways of regulating itself. The oceans will absorb carbon dioxide. Plants will grow more vigorously, drawing carbon dioxide out of the air. Chemical weathering will lock carbon dioxide from the atmosphere into rock. Over tens of thousands of years, carbon dioxide levels would fall back toward their natural range. At that point, the Milankovitch cycles would take over again. Earth's orbit is moving toward a more flattened ellipse over the next 20,000 to 30,000 years. The axial tilt will decrease, making summers cooler. All the signals point toward the gradual onset of another ice age. If this scenario unfolds, ice would begin accumulating in the Arctic in roughly 10,000 to 15,000 years. Slowly, very slowly, but relentlessly. Snow would fall and fail to melt completely in summer, building layer upon layer of ice. The ice sheets would spread. From Canada, from Scandinavia, the glaciers would advance southward. The real challenge is that by then the world could have 8 billion, 9 billion, perhaps 10 billion people. We cannot live through an ice age the way hunter-gatherer ancestors once did. We depend on agriculture, on cities, on global supply chains. An ice age would disrupt everything. Farming across Canada, Russia, Northern Europe, and northern parts of North America would no longer be viable. These are among the largest food-producing regions on Earth. Losing them would mean losing the ability to feed billions. People would be forced to migrate south toward regions closer to the equator. But equatorial areas are already densely populated. There would not be enough space for everyone. Conflicts would erupt, wars over food, water, and land. Famine would spread. Populations would decline sharply. Could technology help us survive? Perhaps we would grow crops in greenhouses, raise fish in tanks, manufacture synthetic food. Perhaps we would build underground cities, heated by nuclear energy, living beneath the ice. But all of this remains speculation. Humanity has never attempted to endure an ice age with 8 billion people.
The third scenario, the most frightening of all, is one where the climate system slips into chaos, unpredictable and beyond our control. Earth's climate is extraordinarily complex. It does not shift in smooth, linear ways. It has tipping points, thresholds that, once crossed, trigger sudden changes that cannot be reversed. We have seen this before with the Younger Dryas, a glacial lake burst, ocean currents stalled and the climate flipped within a few years, like a switch turning on and off. Today, we may be pushing several such switches toward their breaking points. Greenland's ice is melting. If a large volume of meltwater pours rapidly into the North Atlantic, it could disrupt the ocean's overturning circulation, just as it did during the Younger Dryas. But this time, the cause would not be natural cycles, it would be us. Northern Europe could plunge into deep cold, even as the rest of the world warms, a bewildering contradiction. West Antarctica rests on bedrock below sea level, held back by floating ice shelves along its edges. If those shelves collapse, the ice behind them could slide into the ocean far more quickly, possibly within just a few decades. Sea levels could jump by 3 to 5 meters with little warning, leaving no time to adapt. The frozen soils of Siberia, Canada, and Alaska, known as permafrost, are thawing. Permafrost contains enormous stores of carbon from plants that have been frozen for thousands of years. As it thaws, microbes break down this ancient organic matter, releasing carbon dioxide and methane. Methane is a greenhouse gas about 25 times more powerful than carbon dioxide over the first 100 years after it is released. If permafrost were to thaw extensively, it could release methane equivalent to several 100 billion tons of carbon dioxide, an immense amount, enough to push global temperatures even higher by several more degrees Celsius. Rising temperatures thaw more permafrost. Thawing permafrost releases more methane. Methane drives temperatures higher still, a self-reinforcing loop with no clear stopping point. The Amazon rainforest is under a double strain: deforestation from human activity and drying driven by climate change. Rainforests depend on rainfall to survive, yet the forest itself helps generate rain through the evaporation of water. If too much forest is lost, rainfall declines. The remaining forest becomes drier and more vulnerable to fire. Wildfires release carbon dioxide, making the climate hotter and drier still. Scientists worry that the Amazon could reach a tipping point, shifting from rainforest to dry savanna within just a few decades. At that point, instead of absorbing carbon dioxide, it would release it, a vast carbon sink transformed into a carbon source. All of these tipping points could interact. Melting ice alters ocean currents. Changing currents reshape regional climates. Climate shifts accelerate permafrost thaw. Thaw releases methane. Methane speeds up ice loss. Forests transition into grasslands. Grasslands burn and release carbon dioxide. Carbon dioxide drives further warming and melting, a chain reaction like falling dominoes, each piece toppling the next. Once it begins, there may be no way to stop it. The climate system could become fully unstable, swinging wildly, impossible to predict. In such a scenario, we would not know what comes next. The planet might warm by 4, 5, or 6 degrees Celsius within a few decades. Some regions could become unbearably hot, effectively uninhabitable. Others might turn sharply colder as ocean circulation shifts. Extreme storms could batter one region while prolonged drought grips another. Agriculture could falter because seasons become too unpredictable. Ecosystems could unravel under the strain of rapid change. Mass extinctions could follow, not only among wild species, but also among the organisms we depend on: pollinating bees, soil-building earthworms, nitrogen-fixing microbes. This is the worst-case scenario. We hope it never comes to pass, but the possibility is not zero. We are conducting a vast experiment on this planet, one no one has ever run before, and we do not know how it will end. 3 paths lie before us: delaying the Ice Age but risking excessive warming, an Ice Age arriving while we remain unprepared, or total instability. None of them is comforting. Each presents enormous challenges for humanity. We stand at a crossroads. For the first time in Earth's 4 billion-year history, a single species has the power to reshape the planet's entire climate. It is immense power, and power always comes with responsibility. Are we wise enough to use it responsibly? That is the question of this century, perhaps the question of the millennium.
Glaciers teach us the most important lesson of all, a lesson we need to carve deep into our minds. Earth may look strong, solid, unchanging, but in truth, it is incredibly fragile. The Younger Dryas is a warning. A lake burst through its natural dam, that's all. A single event, unfolding over a short span, perhaps only a few months. Fresh water poured into the ocean. In less than 10 years, the entire northern hemisphere slipped back into an ice age climate. 10 years. A child born into a warming world could reach the age of 10 already living in a frozen one. Summers no longer felt warm, snow never fully melted, plants slowly died off, animals disappeared, human life changed completely. That cold period lasted more than 1,000 years. 50 generations lived in the chill. Then, just as suddenly as it began, temperatures surged upward again. Within 10 years, perhaps less, the climate warmed, snow melted, forests returned, life flourished. What does this tell us? The climate system has switches. These switches can flip very quickly. When the switch is on, it's state A. When the switch is off, it's state B. There is no slow, gentle transition. Change can arrive abruptly, within a decade or less. But returning to the old state, that's another story. The Younger Dryas lasted over 1,000 years before it ended. The system is easy to push into a new state, but extremely hard to pull back. It's like pushing a massive boulder up a hill and then letting it roll down. Pushing it up is hard, rolling down is easy, but getting it back up again, almost impossible. We may be pushing such boulders without realizing it. Greenland's ice is melting. The Atlantic circulation is slowing. Scientists have measured it. The flow is about 15% weaker than it was a few decades ago. It hasn't stopped, but it is slowing. If it stops, the switch flips. Northern Europe would cool abruptly, possibly dropping 10 to 15 degrees Celsius within 10 years. London could feel like Reykjavik, Paris like Oslo, Barcelona like Copenhagen, all within a single generation. Could we restart the circulation? Could we make it flow again? No one knows. It might take thousands of years for the system to rebalance itself. It might never return if we push it too far. This is fragility. The system looks stable, looks powerful. Then a small shove and it tips into another state. There are no clear warnings, no signposts saying, danger, tipping point ahead. You only realize it when it's already too late. Scientists call this hysteresis. A system can have multiple stable states. When it's in state A, it takes a great deal of energy to push it into state B. But once in B, it takes just as much energy to return to A. The system has memory. It remembers where it is and prefers to stay there. Earth is not a passive machine that responds smoothly to outside forces. It is a dynamic system with multiple stable states, countless feedback loops and tipping points. Push it a little and nothing may happen. Push past a threshold and everything changes dramatically with no way back. We may be pushing such boulders without realizing it. Greenland's ice is melting. The Atlantic circulation is slowing. Scientists have measured it. The flow is about 15% weaker than it was a few decades ago. It hasn't stopped, but it is slowing. If it stops, the switch flips. Northern Europe would cool abruptly,
possibly dropping 10 to 15 degrees Celsius within 10 years. London could feel like Reykjavik, Paris like Oslo, Barcelona like Copenhagen, all within a single generation. Could we restart the circulation? Could we make it flow again? No one knows. It might take thousands of years for the system to rebalance itself. It might never return if we push it too far. This is fragility. The system looks stable, looks powerful. Then a small shove and it tips into another state. There are no clear warnings, no signposts saying, danger, tipping point ahead. You only realize it when it's already too late. Scientists call this hysteresis. A system can have multiple stable states. When it's in state A, it takes a great deal of energy to push it into state B. But once in B, it takes just as much energy to return to A. The system has memory. It remembers where it is and prefers to stay there. Earth is not a passive machine that responds smoothly to outside forces. It is a dynamic system with multiple stable states, countless feedback loops and tipping points. Push it a little and nothing may happen. Push past a threshold and everything changes dramatically with no way back. We don't know exactly where those thresholds lie. We only know they exist. And we are pushing the system, pushing hard, pushing fast. We hope we haven't crossed any of them yet. But hope is not a strategy.
Glaciers also teach us about connection. Everything on Earth is linked in surprising, intricate ways, often in ways that feel counterintuitive. Earth's orbit shifts out in space. That affects the ice in the Arctic. Arctic ice influences the Sahara Desert. The Sahara expands when the climate is cold and shrinks when it is warm. Winds sweep across the desert, carrying dust with them. The dust travels across the Atlantic, settling into the ocean. The dust contains iron. Iron feeds plankton. Plankton photosynthesize, drawing carbon dioxide out of seawater. Less carbon dioxide in the water means more carbon dioxide is pulled from the atmosphere. Less carbon dioxide in the atmosphere means a cooler Earth. Cooler temperatures mean more ice in the Arctic. More ice means the Sahara expands even further. A long chain stretching from outer space to the Arctic, to North Africa, to the Atlantic, to microscopic life, and back again to shape the climate of the entire planet. Who would imagine that dust from the Sahara could influence ice in Antarctica? And yet it does. The data shows it clearly. Or consider the great ocean circulation. Warm water from the tropics flows into the North Atlantic. It cools, sinks, moves along the ocean floor toward Antarctica, then passes through the Indian Ocean and the Pacific, rises again, warms, and flows back. One enormous loop that takes 1,000 years to complete. This circulation shapes the climate of many regions. Northern Europe stays mild because warm water arrives there. Peru is cool because cold water wells up from the deep. The Amazon receives heavy rainfall because moisture evaporates from the warm Atlantic. The Sahara remains dry because winds blowing off the desert toward the ocean carry little moisture. If the circulation shifts, all of these places shift with it, not just one region, but the entire planet. A change in the North Atlantic can trigger a global domino effect. Or think about forests. Forests do not simply stand still absorbing carbon dioxide. They create rain. Trees draw water from the soil and release it through their leaves. Water vapor rises, forms clouds, and falls as rain. The Amazon generates most of its own rainfall. Without the forest, there is no rain. Without rain, the forest dies. But forests also shape distant places. Moisture from the Amazon travels to the Andes Mountains, falling as snow at high elevations. This snow melts into rivers that sustain millions of people in Peru, Bolivia, and Chile. Without the Amazon, there would be no snow in the Andes and no reliable water for agriculture across much of western South America. Or consider Arctic sea ice.
When sea ice melts, darker ocean water is exposed, absorbing more sunlight, warming further, and causing more melting. A self-reinforcing loop. But it does not stop there. Melting sea ice alters wind patterns. Shifting winds change the paths of storms. Storms move differently, rain falls in new places, drought appears where rain once came regularly. A small change in the Arctic can contribute to drought in California, flooding in Pakistan, or unusually cold winters in Texas. Everything is connected through the vast network of the atmosphere and the oceans. The idea that a butterfly flapping its wings in Brazil could help set off a tornado in Texas is often used as a metaphor for the butterfly effect. But in the case of Earth's climate, it is not just a metaphor, it is reality. Small changes in one place can genuinely produce large consequences far away through chains of connection. The lesson is simple. Nothing exists in isolation. Nothing affects only one place. Everything influences everything else. Earth is a single, global, tightly integrated system. When we release carbon dioxide into the atmosphere, we are not just warming the air, we are altering ice, oceans, forests, deserts, winds, rain, everything. We are tugging on threads in a complex web without knowing which threads connect to which, or what pulling one thread might do elsewhere in the network. This is why predicting the future is so difficult. We can calculate that if carbon dioxide rises by some amount, temperature will rise by another. But how many feedback loops will that warming trigger? How will those loops interact? What will the final outcome be? No one can say with certainty. Computer models try to simulate all of these interactions. They grow more sophisticated, more accurate with time. But they are still not perfect. Surprises remain. There are still things we do not fully understand.
The final lesson, perhaps the most important of all, is about time. In a natural ice age cycle, everything changes slowly. Ice takes 50,000 years to advance from the Arctic all the way down to Illinois. 50,000 years, about 2,000 generations. During that time, animals can migrate. They gradually move south, following the climates they prefer. Each generation shifts a little. Nothing is sudden. Nothing moves too fast. Plants follow a similar pattern. Trees cannot walk, but their seeds can travel far. Each year, forests expand a few meters southward. Over a few thousand years, an entire forest can shift thousands of kilometers. Slow, but fast enough to keep up with the changing climate. Life has time to evolve. Individuals better suited to the new conditions survive and reproduce. Those that cannot adapt are filtered out. Over many generations, species change. Fur grows thicker, bodies grow larger, colors shift. Evolution works best when there is time. Humans are no exception. Our ancestors survived ice ages because they had time. They watched the ice advance gradually. They slowly moved south. They learned to hunt new animals, eat new foods, live in new environments. Each generation learned and passed knowledge on. Understanding accumulated. Culture evolved. But today's changes are different. They are unfolding over a few decades, not a few thousand years. Roughly 100 times faster than natural rates. In natural cycles, over 100 years, carbon dioxide rises by about 1 part per million. Over the past 100 years, it has risen by 50 parts per million, about 50 times faster. Temperature tells a similar story. In natural cycles, over 100 years, temperatures rise by about 0.01 degrees Celsius. Over the past 100 years, they have risen by about 1.1 degrees Celsius, roughly 100 times faster. Living things do not have time. Plants cannot move quickly enough. Forests need thousands of years to shift thousands of kilometers, but the climate is changing within decades. Forests die where they stand, unable to relocate in time. Animals face the same challenge.
Some species can move quickly, migrating toward the poles or up mountains, but many cannot. They become trapped. Their habitats disappear too quickly. They cannot find new homes. They go extinct. Evolution requires time, many generations. When climate shifts within decades, there are only a few generations, not nearly enough time to develop new traits. Species that cannot adapt disappear, and there are no replacements. Ecosystems unravel. And what about us? Humans are more flexible. We have technology. We can build seawalls against rising oceans, relocate cities, change crops. But all of this costs money, effort, and time. Rapid change creates strain. Farmers must switch crops, yet they do not know which crops will suit the new climate because the climate keeps shifting. Coastal cities must build defenses, yet they do not know how high to build because sea levels continue to rise. People must move, but where do they go when everywhere is changing? Then there is society itself. Fast change breeds instability. Failed harvests lead to hunger. Hunger leads to unrest. Unrest can lead to war. Large migrations spark conflicts over resources and land. Political tension rises. Populism grows. Authoritarianism finds fertile ground. History shows that periods of rapid climate change often coincide with social turmoil. Time is a double-edged sword. With time, living things adapt. Societies adjust. People find solutions. Without time, systems break down. Natural ice ages provide time. Human-driven climate change does not. This may be the most important lesson of all. The problem is not simply that we are warming the Earth, it is that we are warming it too quickly. Speed is the issue. The Earth has been warmer before in its history, but it has never warmed this fast. Species, ecosystems, even human societies cannot adapt quickly enough. We need to learn how to slow down, to reduce the pace of change, to give the Earth, other living beings, and ourselves the time needed to adapt. That is the difference between survival and collapse.
Now zoom out, far out, beyond the ice ages, beyond the dinosaurs, all the way back to when Earth itself was just being born. Earth formed about 4.5 billion years ago. That number is so vast it's almost impossible for the human brain to grasp, so let's compress it. Imagine the entire 4.5 billion year history of Earth squeezed into a single day, 24 hours. Earth forms at midnight, a molten sphere constantly battered by meteorites. The surface is an ocean of lava. There is no air, no water, no life. Around 4 in the morning, the surface cools enough for water vapor to condense. Oceans form. There is still no life, but the stage is set. Around 6 in the morning, life appears. Simple bacteria living in hot water near volcanic vents on the ocean floor. They don't need oxygen, they feed on chemicals from the volcanoes. From 6 in the morning to 8 in the evening for 14 straight hours, there is nothing but bacteria. No plants, no animals, no fish, no insects, just bacteria. 14 hours out of a 24-hour day, nearly 60% of Earth's history is microbial. Around 2 in the afternoon, a special kind of bacteria evolves. They learn to photosynthesize using sunlight, absorbing carbon dioxide, releasing oxygen. Slowly, very slowly, oxygen begins to accumulate in the atmosphere. Most organisms at the time see oxygen as a poison. Many die, but some adapt, learning to use oxygen for respiration, unlocking far more energy. Around 8 in the evening, the first multicellular organisms appear. Cells begin cooperating, forming larger, more complex life. Sponges, jellyfish, worms. Still no bones, still no hard shells. Around 9 in the evening comes the Cambrian explosion. Suddenly, over a span of a few tens of millions of years, nearly all major animal groups appear. Creatures with shells, with eyes, with limbs, trilobites, shrimp, crabs, snails. The oceans burst with life.
Around 10 in the evening, plants crawl onto land. Before this, the continents are completely barren, just rock, no trees, no grass, no moss. The first plants are small, hugging the ground. Gradually, they grow taller, larger. Primeval forests take shape. Around 10:30 in the evening, animals follow plants onto land. Insects, scorpions, then amphibians and reptiles. The continents transform from lifeless deserts into thriving ecosystems. Around 11 in the evening, dinosaurs appear. They dominate Earth for 12 minutes on this 24-hour clock. 12 minutes corresponds to about 165 million real years. Dinosaurs flourish, diverse and widespread across land and sea. Around 11:39 in the evening, a giant asteroid slams into Earth near what is now Mexico. The explosion is catastrophic. Dust blocks the sun. Temperatures fall. Dinosaurs gradually die out. Most large species vanish, but some small creatures survive, including the ancestors of mammals. From 11:39 in the evening to 11:58 in the evening, mammals diversify and spread. Mice, dogs, cats, horses, elephants, whales, bats, monkeys, all evolving from those small survivors of the dinosaur extinction. At 11:59 and 53 seconds in the evening, primates appear, the ancestors of monkeys and humans, living in trees, eating fruit. At 11:59 and 50 seconds in the evening, humans split from our common ancestor with chimpanzees. We begin becoming a distinct species. At 11:59 and 56 seconds in the evening, modern humans, Homo sapiens, appear in Africa, 4 seconds before midnight. At 11:59 and 59.9 seconds in the evening, the last ice age ends. Agriculture begins. Civilization emerges, the final second of the day. At 11:59.999 seconds in the evening, the Industrial Revolution, the final 0.1 second. All recorded human history from ancient Egypt, from Mesopotamia, from China, from Greece and Rome unfolds within just the last 0.2 seconds of the day. Your life, if you live 80 years, is about 0.000002 seconds on this scale, shorter than a blink. That number makes us feel small, insignificant, yet within that final 0.1 second, we have changed the entire planet. We have created impacts greater than the asteroid that wiped out the dinosaurs, at least in terms of the speed of change. We are a tiny dot in Earth's history, but this tiny dot is leaving an enormous mark. Future geologists, looking at rock layers from our time, will see it clearly. Layers of plastic, concrete, metals, radioactive traces from nuclear weapons, fossil remains of domesticated chickens and pigs outnumbering all wild animals. They will see carbon dioxide concentrations soaring. They will see mass extinctions. They will know that something happened, a major event. They may call it the Anthropocene, the age of humans, a geological boundary as clear as the one that marks the extinction of the dinosaurs.
But there's something astonishing when you look at Earth's long history. Life is incredibly resilient. Life always finds a way. Our planet has endured periods of unimaginable hardship, times far worse than anything we are experiencing today. Around 700 million years ago, Earth went through what scientists call the snowball Earth event. Ice didn't just cling to the poles, it covered the entire planet, from one pole to the other, even across the equator. The oceans froze to depths of hundreds of meters. Sunlight was almost completely reflected back into space. Temperatures plunged to -40, -50 degrees Celsius across the globe. This phase lasted for millions of years. Photosynthesis nearly stopped because ice covered almost everything. Oxygen levels were extremely low. Life retreated into a few tiny refuges, deep-sea hydrothermal vents, where water remained liquid and chemicals from Earth's interior provided energy. Life should have died out, but it didn't. It clung on. It endured. Volcanoes kept erupting. Carbon dioxide built up in the atmosphere because there were no plants to absorb it. After millions of years, enough carbon dioxide accumulated to warm the planet again. The ice melted. Life surged back, more vigorous than ever.
It was after Snowball Earth that multicellular animals truly began to flourish. Or consider the 5 mass extinctions. 5 times in Earth's history, more than 70% of species disappeared in relatively short periods. The Ordovician extinction, about 445 million years ago, wiped out about 85% of marine species. The Devonian extinction, around 375 million years ago, eliminated roughly 75% of species. The Permian extinction, 252 million years ago, the largest of all, erased 96% of marine species and 70% of land species. Earth came close to total collapse. The Triassic extinction, about 201 million years ago, saw about 80% of species vanish. The Cretaceous extinction, 66 million years ago, ended the dinosaurs, along with about 75% of all species. Each time, life was struck down severely. Ecosystems collapsed, oceans turned toxic, the atmosphere filled with harmful gases, temperatures swung wildly. It seemed like the end of everything. Yet, each time, life returned. The survivors, however few, began to multiply. They filled the empty niches left behind. They evolved into new, strange, diverse forms. After a few million years, Earth was once again vibrant, sometimes even more diverse than before the extinction. Extinction is catastrophe, but extinction also opens doors. After the dinosaurs disappeared, mammals finally had the chance to rise. Without that extinction, we would not exist. Life always finds a way. No matter how harsh the environment, no matter how many species vanish, some always endure, survive, and recover. Life as a whole is not easily erased, but there is one crucial difference. Past extinctions were driven by natural causes, massive volcanic eruptions, asteroid impacts, extreme glaciations. No single species caused them. This time is different. This time, one species is responsible. Us. We are creating the 6th mass extinction. The current rate of extinction is between 100 and 1,000 times faster than the natural background rate. Every day, dozens of species disappear. Every year, thousands are lost. Not because of an asteroid, not because of volcanoes, but because humans cut down forests, overfish the oceans, pollute the environment, and alter the climate. Life will survive this extinction, almost certainly. Bacteria will be fine. Insects will likely survive. Some plants, some fish, some small animals will endure. They will survive, evolve, and repopulate the planet. No matter what humans do, in a few million years, Earth will likely be green and thriving again. But will humans be among the survivors? That is the real question. Life in general will be okay. But what about us, Homo sapiens? Will we be okay? We are not bacteria that can live in extreme environments. We are not cockroaches that can eat almost anything. We are a highly specialized species, dependent on complex ecosystems, dependent on a stable climate, dependent on agriculture, dependent on society. When systems collapse, we collapse with them. Yes, we have technology, but technology depends on systems too. Without electricity, without fuel, without supply chains, technology becomes little more than scrap metal. So this is the lesson we must take from deep history. Life as a whole is resilient, but individual species are fragile. Dinosaurs ruled for 165 million years, then vanished within a geological instant. Mammoths survived multiple ice ages, then went extinct about 4,000 years ago. No species is immortal. No species is guaranteed forever. We have existed for less than 300,000 years. On the geological scale, we are very young. Can we last another 300,000 years? Another million? Or will we become one of the early extinctions, leaving behind only thin layers of fossils for future geologists to discover? The answer depends on what we do right now. The choices we make over the next couple of decades could shape the fate of our species for millions of years to come. It is a heavy responsibility, but it is also an extraordinary opportunity.
Looking toward the future, it's easy to feel unmoored.
Too much uncertainty, too many variables, too many things we simply don't know. But in the middle of all that ambiguity, there are a few things we do know for sure. Let's start there. The first thing we know with certainty is that the Milankovitch cycles are still at work. Earth's orbit continues to change according to the mathematical patterns Milankovitch calculated. Nothing about this has changed. Earth still circles the sun, its axis is still tilted, still gently wobbling. The cycles of 23,000 years, 41,000 years, and 100,000 years continue to unfold. Right now, we are in a phase where Northern Hemisphere summer occurs when Earth is farthest from the sun. This makes summers in the Northern Hemisphere slightly cooler. Over the next few thousand years, this trend will continue. Summers will grow cooler still. Without any other interference, snow will begin to accumulate in the polar regions. Ice will start to expand. The next ice age would begin. The second thing we know for sure is that carbon dioxide levels in the atmosphere have risen to levels not seen in several million years, from 280 parts per million before the Industrial Revolution to 420 parts per million today. This number is not a guess. It is measured precisely at stations around the world and verified by thousands of scientists. We also know exactly where this carbon dioxide comes from: the burning of fossil fuels. We know because carbon from fossil fuels carries a distinctive isotopic signature, different from carbon from natural sources. When we measure carbon isotopes in the atmosphere, we clearly see the fingerprint of fossil fuels. The third thing we know is that Earth is warming. The global average temperature has risen by about 1.1 degrees Celsius since the late 19th century. Again, this is not speculation. Thousands of temperature stations across the world, on land and at sea, everywhere you look, all show the same warming trend. We can also see the consequences of this warming. Melting ice is measured by satellites, by aircraft, and by people taking direct measurements on the ground. Rising sea levels are tracked by monitoring stations along coastlines worldwide. Shifting seasons are recorded by farmers and biologists alike. All the data lines up. The fourth thing we know for certain is that carbon dioxide is a greenhouse gas. This is not controversial. It was demonstrated in laboratory experiments back in the 19th century. You can test it yourself. Shine light through a tube filled with carbon dioxide and measure how much heat is retained. More carbon dioxide, more heat trapped. It's that simple. Basic physics tells us that carbon dioxide absorbs infrared radiation, the kind of radiation Earth emits as it releases heat into space. More carbon dioxide means less heat escapes, which means a warmer planet. There is nothing mysterious about it, nothing to debate. Put these four facts together and we arrive at a clear conclusion. Humans are warming the planet by releasing carbon dioxide from burning fossil fuels. This is not an opinion, not a theory. It is a reality supported by mountains of data and accepted by 99% of scientists who study climate. People who deny climate change often say that the science isn't settled or that there's still debate. But the debate is not about these fundamentals. These are certain. The discussion is only about the details: how much temperatures will rise, where rainfall will change, which species may go extinct. Those questions truly do carry uncertainty, but the big picture is clear.
But the more we learn, the more we realize how little we truly know. There are still enormous questions without clear answers. The first question is, where are the tipping points? We know they exist. We know the climate system has thresholds. Once crossed, things can change suddenly. But we do not know exactly at what temperature those thresholds lie. At what temperature would the Greenland ice sheet melt completely, beyond the point of no return? Some studies say 1.5 degrees Celsius, others say 2 degrees Celsius, others say 3 degrees Celsius. We are not sure. It is possible we have already crossed that threshold without realizing it. It is also possible we still have time. When will permafrost release vast amounts of methane? It is already thawing, we can see that. But will the methane released be enough to trigger a self-reinforcing feedback loop, or will it thaw slowly, giving us time to adapt? No one knows for certain.
Could the Amazon shift from rainforest to savanna? At what level of deforestation, at what level of dryness would the tipping point arrive? Some models suggest 40% forest loss. Right now, about 20% has been lost. We are getting close, but the real threshold might be 50%, 60%, or it might be 30%, and we are already nearing it. The trouble with tipping points is that you only know you have crossed them after the fact. It is like walking through fog near a cliff. You cannot see the edge until you step beyond it, and by then it is too late. The second question is, which feedback mechanisms are strongest? We know there are many feedback loops. Melting ice reduces reflection, which causes more warming, which melts more ice. Rising carbon dioxide causes warming, which leads the oceans to release more carbon dioxide. Thawing permafrost releases methane, which causes more warming, which thaws more permafrost. But there are also negative feedbacks that slow change. More carbon dioxide can make plants grow faster, absorbing more carbon dioxide. Warmer oceans can absorb more carbon dioxide. Clouds might increase, reflecting sunlight and cooling the planet. Which loops will dominate, positive or negative? Will the system amplify itself or stabilize? This is a trillion-dollar question. Computer models try to account for all these loops, but each model produces slightly different results. Some project warming of 2 degrees Celsius by the year 2100. Others project 4 degrees Celsius. The difference is enormous. The problem is that we have never run this experiment before. Earth has never had 8 billion people emitting carbon dioxide at this rate. We are doing something unprecedented. There is no historical data to fully validate the models. We are flying through fog, relying on a compass that is not perfectly calibrated. The third question is, what will humans do? This may be the most uncertain of all. Natural science is complex, but it still follows the laws of physics. Humans are unpredictable. Will we cut emissions? Shift to renewable energy? Stop cutting down forests? Some countries are doing this. Others are not. Some are increasing emissions. The global trend is still unclear. Will technology save us? Solar power keeps getting cheaper. Batteries keep improving. Electric vehicles are becoming more common. Perhaps in 20 years, most energy will come from renewable sources. Perhaps we will invent ways to pull carbon dioxide out of the atmosphere and store it back underground. Perhaps, or perhaps not. Perhaps we will continue burning coal and oil because they are cheap, familiar, because change is difficult. Perhaps major nations will fail to cooperate, each waiting for the others to act first. Perhaps we will not move fast enough. No one knows. The future is not written. It depends on choices, billions of small choices made by billions of people, whether to buy an electric car or a gasoline car, whether to turn on the air conditioner or use a fan, whether to eat more or less meat, which politicians to vote for, where to invest money. All of it matters. Will the next ice age never arrive? Or will it come but we will be different by then? Or will we create something entirely new, something never before seen in Earth's history, a planet influenced by a conscious species with technology, with the ability to adjust the climate intentionally? It sounds like science fiction, but we are already on that path. We have changed the climate unintentionally. Could we change it deliberately? Keep temperatures stable? Prevent glaciation indefinitely? Or even shape the weather? Bring rain when needed? Hold back storms when we choose? Some people dream of that future. Others fear it, fearing we might break something beyond repair. Both could be true. What is certain is that we are at a crossroads. The decisions made in the next couple of decades will shape thousands, perhaps millions of years to come. That is immense power, and it is also immense responsibility. We are the first generation to truly understand what we are doing to this planet. We are the last generation with a real chance to change course. The pressure is immense, but so is the opportunity. How will history remember us? As the generation that destroyed the planet? Or the generation that saved it? Or simply the generation that lived through a transition, did its best but not enough, leaving the rest for those who came after?
Now, as our journey draws to a close, let's take one last moment to reflect on our unusual place in time. We are living in a rare moment, a pause between two frozen worlds. Over the past 2 million years, Earth has passed through dozens of ice edges. Each one lasted roughly 90,000 years. Between them came brief warm intervals, each lasting only about 10,000 to 15,000 years. A simple calculation shows that we exist in warm conditions only about 10 to 15% of the time. For most of history, roughly 85 to 90%, Earth has been locked in ice. If you had been born at a random moment, any time over the last 2 million years, chances are you would have arrived during an ice age. You would have seen ice instead of forests, hunted mammoths instead of growing wheat. But we are fortunate. We were born within that 10 to 15% of warmth. And more than that, we were born during the most stable warm period yet. Over the last 10,000 years, since the end of the last ice age, global temperatures have fluctuated within an unusually narrow range, about 1 degree Celsius up or down. The climate has been remarkably steady. It is not by accident that civilization emerged during this stability. Agriculture depends on predictable weather. You cannot farm if you do not know which seasons bring rain, which bring sun, which bring cold. You need the ability to anticipate the rhythms of the years. The past 10,000 years made that possible. From agriculture came villages. From villages came cities. From cities came civilization. Writing, mathematics, science, art, all of it arose within this 10,000-year window. All of it made possible by a stable climate. We are not only lucky to live in a warm period, we are even luckier than that. We live at a time when humanity has developed enough to understand this planet, yet it is not too late to do something about what we see. 100 years ago, we did not know about ice ages. We did not understand the Milankovitch cycles. We did not recognize carbon dioxide as a greenhouse gas. We were reshaping the planet without realizing it. 100 years from now, it may be too late. We may have crossed too many tipping points. The Greenland ice sheet may have melted beyond recovery. Permafrost may have released vast amounts of methane. The Amazon may have shifted into savanna. At that point, no matter what we try, reversal may no longer be possible. Right now, in the year 2026, we occupy a unique position. We know enough to understand the problem. We possess the technology to address it. We still have time. Not much, but some. The window of opportunity is open, yet it is closing day by day. Our generation did not choose to be born into this moment, but here we are, standing at a crossroads in history, at a decisive turning point. What we do or fail to do in the coming decades will echo across thousands of generations to come.
Look ahead, far ahead. 10,000 years, 100,000 years. Someone will look back at our time. What will they see? If they are geologists, they will dig down into rock layers from the 20th and 21st centuries. They will find something strange, a thin but unmistakable layer. They will find plastic, billions of tons buried everywhere. Plastic does not break down. It can persist for millions of years. Water bottles, shopping bags, toys, computer casings, all of it will remain as plastic fossils. No geological layer before this one contains plastic, only this layer does. They will find concrete, mountains of it, from skyscrapers, bridges, roads, and dams. Concrete is durable, It endures for a very long time. A global layer of concrete, a clear signature of an industrial civilization. They will find refined metals, aluminum, copper, iron, titanium. In nature, metals rarely exist in pure form. They are mixed with soil, rock, and rust. But humans refine them. We create pure metals to build cars, airplanes, and phones. When these objects are buried, the metals remain, an unmistakable sign of intelligence. They will find radioactivity, traces from nuclear weapons tests in the 1950s and 1960s. Radioactive particles spread across the planet, settling into soil and becoming part of the rock record. A global radioactive layer, evidence of a species that learned to harness atomic energy. They will find fossils, chicken fossils, pig fossils, cow fossils, in staggering numbers, more than all wild animals combined. Because we raise far more chickens, pigs, and cattle than the number of wild animals left on Earth. Someone in the future will see it clearly. Humans dominated the biosphere. They will also notice what is missing: fossils of countless species that disappeared abruptly at the same moment. A mass extinction, the sixth extinction event. Not caused by an asteroid this time, not by volcanoes, but by a single species. They will analyze ice cores, if any ice remains. They will see carbon dioxide concentrations rising sharply from 280 parts per million to 420, perhaps 500 or 600 parts per million if we do not stop. The fastest increase in millions of years. They will know something extraordinary happened. They will uncover traces of buried cities, streets beneath layers of sediment, foundations hidden underground, tunnels running below. They will excavate artifacts, phones, computers, cars, airplanes. They will marvel at the complexity. They will give this layer a name, perhaps the Anthropocene, the age of humans, a clear boundary in Earth's history. Before the Anthropocene, dinosaurs ruled for 165 million years before vanishing. During the Anthropocene, humans ruled for how long? The answer is still unknown. How will the story end? What will they find in the layers above the Anthropocene? They might find signs of recovery. Humanity learned. We stopped burning fossil fuels. We restored forests. We learned to live sustainably with the planet. Carbon dioxide slowly declined. Temperatures stabilized. Life rebounded. Humanity endured for millions more years, spreading beyond Earth and becoming an interplanetary civilization. Or they might find collapse. We did not stop in time. Temperatures rose too high. Systems failed. Civilization unraveled. Populations fell sharply. Humans retreated into small hunter-gatherer groups, like our ancestors 20,000 years ago. Or worse, humanity vanished entirely, leaving behind only decaying remnants. Or they might find something completely different, a future we cannot yet imagine. Humans merging with machines, evolving into a new species, or creating new forms of life to inherit Earth. Science fiction made real. We do not know how the ending will unfold, but we do know this: we are writing it right now. Every choice is a sentence. Every action is a paragraph. We are the authors of the future.
That's it. You've come with me on this long journey, from the strange stones in the Alpine valleys, from a curious carpenter named Jean-Pierre Perrodin, to the astonishing discovery of the 100,000-year cycle, to the mysteries that remain unsolved, to a future no one can be certain about. Now, as you lie here, ready to drift into sleep, let these thoughts settle gently. Remember that you are resting on a remarkable planet, a planet circling a star, spinning through space, tilting back and forth, swaying like a slowing top. A planet whose orbit shifts shape over a cycle of 100,000 years, from nearly circular to more elliptical and back again, in a cosmic dance that never truly stops.
a planet that freezes and thaws, cools and warms, following the rhythm of the stars, guided by laws of physics we are only beginning to understand. You are living in a rare, warm moment between icy worlds, a special moment, a gift from the universe. Every breath you exhale carries carbon. That carbon may have come from an ancient tree that lived thousands of years ago, or from tiny plankton that died in the ocean, or from dinosaurs that walked this land 100 million years ago. Carbon cycles endlessly, from the air into plants, from plants into animals, from animals into the soil, and from the soil back into the air, an unbroken circle. Every sip of water you drink has been a cloud, rain, river, sea, ice in Antarctica, the sweat of dinosaurs, the tears of people long gone. Water moves in an eternal cycle. We drink the very same molecules our ancestors drank thousands of years ago. Every atom in your body was forged in the heart of a star. Stars that died billions of years ago exploded and scattered these atoms across the cosmos. Those atoms gathered, forming Earth, forming you. You are stardust, literally, not poetry, but scientific truth. You are not separate from this planet. You are part of it, part of the carbon cycle, the water cycle, the cycle of matter. You are Earth experiencing itself, observing itself, wondering about itself. The ice will return, or it won't. We don't know. Perhaps in 10,000 years, perhaps never. The cycle may continue, or perhaps we have rewritten the script. The world will change. It always does. Nothing stands still. Nothing lasts forever. Ice comes and goes, seas rise and fall, mountains rise and erode, continents drift, species evolve and vanish. All of it is part of the great flow of time. But right now, in this moment, you are here, on warm, comfortable ground, in a rare era when the ice has retreated, when the climate is relatively stable, when life flourishes. At a special time, when humanity is wise enough to understand the universe, yet still humble before its power. A place where the ice has stepped back, leaving land for us to live. A place where the future remains open, undecided, still full of hope. Sleep well. Let the great cycles keep turning. Let Earth continue spinning through space. Let time continue to flow, slowly, patiently, without hurry. When you wake tomorrow morning, sunlight will shine through your window. That light has traveled 150 million kilometers through space, taking 8 minutes and 20 seconds to reach you. It has warmed this planet for 4.5 billion years, and it will continue to do so for another 5 billion years. Remember, every day is a gift from 4.5 billion years of planetary formation, from hundreds of thousands of ice age cycles that came before, from millions of generations of living beings that lived, died, and evolved to make you possible, from countless fortunate coincidences that happened at just the right time, from a vast universe that seems endless, yet this planet, this Earth, is the only place we know where life exists, all leading to this moment, to you. The world will continue to change. Ice may return or not. The climate may stabilize or not. Humanity may endure for millions more years or not. Much depends on the choices we make. But whatever the future holds, you were here. You lived. You were part of this great story, a story that began with the Big Bang, traveled across billions of years, through millions of generations, through countless wonders, to arrive at this moment. The moment you lie here, listening to a story of ice ages, of the 100,000-year cycle, of a planet breathing, living, changing. Sleep well. May you dream of ice and fire, of deep time, of great cycles. May you wake with gratitude, grateful to live in this warm era, grateful to be part of the story, grateful that the future remains open. that there is still hope, still time, still us. Good night.